Hi guys, welcome to another past question on stability. Now we're going to apply what we've learned so far to solve this particular question on stability. Now you're given the open loop transfer function of a system as g of s is equal to k divided by s into s plus 4 then s plus 5, certainly a type 1 system. Now we want to find the restriction on k so that the closed loop system is absolutely stable. So let's dive into this particular problem. Now, if I'm given a problem like this and I want to find the restriction of k such that the system is stable, the first thing I need to do is I see that the system is not in the standard form. So I'll convert the system or the transfer function in this case to standard time constant form. So the standard time constant form for a type 1 system is k all over, you have s then into 1 plus t1s and 1 plus t2s. So this is like the format. We always want to put it in this format. So that's what I'm going to do to this one. So my g of s is going to be k into, so let's look before we solve. So remember that the g of s given to us was something like a 2, sorry, it was a k, I guess, into s bracket s plus 4 and s plus 5. So what we're going to do is to convert it to standard time constant form. I'll have s, then from this bracket I'll factor out 4, so you have dot 4 into, factoring out 4, from 4 you'll be left with 1 plus factoring out 4 from 1s, you'll be left with 1 over 4s. Is that okay? And you do the same thing on this bracket. You factor out 5, then 5 into 5 is 1 plus 5 into 1s will give you 1 over 5s. Is that okay? So this translates, I'll move all these numbers to the numerator position, giving me 1 over 4 dot 1 over 5 k all over s into, you have 1 plus 1 over 4 becomes 0.25 s, then 1 over 5 becomes 1 plus 0.2 s, like this. Is that okay? So my g of s in the standard time constant form is 0.25 times 0.2 k divided by, you have s into 1 plus 0.25 s, and you now have 1 plus 0.2s. So I can let this be, for instance, k naught divided by s into 1 plus 0.25s, and you now have 1 plus 0.2s. So it's better you convert it to this particular form where k naught is equal to 0.25 times 0.2k. Okay, so once we finish our calculations on this form, we'll remember to make this substitution once again. Is that okay? Now the next step is to put s equal to j omega. Okay, put s equal to j omega, then you determine magnitude and phase. So putting s equal to j omega, g of j omega will now become k naught all over, you have j omega here, then you now have 1 plus j 0.25 omega, and we now have 1 plus j 0.2 omega, like this. Is that okay? So you can call this equation 1. Now to find the magnitude of j omega, okay, the magnitude of j omega is going to be k naught. Magnitude of k naught is k naught all over. Magnitude of j omega is only omega. The magnitude of this one will be the square root of 1 plus, you have 0.25 squared omega squared, and magnitude of this one will be square root of 1 plus 0.2 squared omega squared. Is that okay? So when you calculate the magnitude like this, so you can call this equation 2. Now let's calculate the phase. The phase of j omega. Since we are used to calculating the phase, you have the phase of this guy over here is 0 degrees, so you have 0 minus, so it will be phase of this one minus phase of this one minus phase of this one minus phase of this one. That's the standard form. Okay, 0 degrees minus the phase of j omega is going to be 90 degrees. I hope you still remember how it's 90 degrees, and the phase of this one is going to be minus tan inverse of this value divided by 1, which is still the same thing as this value, 0.25 omega, then minus this value divided by 1, and you put it in a tan inverse, okay, of 0.2 omega. So this evaluates to negative 90, okay, minus tan inverse of 0.25 omega minus tan inverse of 0.2 omega. This is equation 3. So after finding the magnitude and the phase, we can now make this statement. Remember, we want to determine the restriction on K to make our system stable. So for the system to be stable, okay, the magnitude of j omega, okay, magnitude of j omega at the phase crossover frequency, okay, must be less than 1. So how many of us remembers why this statement is like this? If you don't remember why, remember that we drew the Nyquist plot of some random system like this, then we drew the unit circle. We called this particular point minus 1, 0. So we called the distance from this point to this one alpha. So from this point to this one, this is the magnitude of this particular function g of s, the magnitude of g of s at a particular frequency WCP. So this frequency must always be the magnitude of g of s at this frequency, which is called the phase crossover frequency, must be less than 1. As you can see, the height of alpha must always be below 1. That's our unit circle, because if alpha is more than 1, then the system will be unstable. But as far as alpha is less than 1, okay, then the system will be stable. That means we need to calculate alpha. So alpha in this case is simply the magnitude of our g of j omega when omega is our phase crossover frequency. So that means we need to calculate the phase crossover frequency, then finally we need to calculate the magnitude. After calculating the magnitude, we'll make it less than 1, and from there we can solve for the value of k, and that's all. So it's the process of determining our omega CP that matters here. So I'm going to show you 2 ways of determining it. If this is your first time of watching my video, please like this channel and subscribe to this channel, and hit the notification bell to stay updated. Now, if this is not your first time, you must have been watching some of the videos I've posted in the past about how to find omega CP. Okay, omega CP is for a type 1 system. Depending on the type of the system, this is a type 1 system. Why is it a type 1 system? Because after converting it to the standard time constant form, we have s raised to the power of 1 occurring. So type 1 system have their parameters. We can calculate this omega CP as 1 over the square root of t1 t2, okay, where t1 t2 are the time constants associated here. This is t1 and this is t2, okay, t1 and t2. Okay, but I'm going to show you another interesting way to still arrive at this answer for those of you that might want to be a little theoretical in exam instead of using formula. So I'll show you how to arrive at this answer, but I'm just going to make this statement as, let's say, equation 4, and for type 1 system, the following formulas hold. The phase crossover frequency is this, and the gain at that crossover frequency, that's why do I keep saying the gain? The magnitude at that crossover frequency when omega is equal to, magnitude is given as k t1 t2 all over T1 plus T2. So this will be relation 5. So we are going to come back to these formulas. But what I'm going to do is I'm going to use another way to get this particular expression. Then I'm going to use this formula to calculate the gain and place my restrictions on K. Is that okay? So can we try that? Very good. So to get this particular expression, you make the statement at phase cross over frequency. Okay, at phase crossover frequency, omega CP 5, 4, 3, 2, 1. The phase of J of J omega is minus 180 degrees. Okay, so what is the phase of J of J omega? We calculated it as minus. This implies that minus 90 degrees minus tan inverse of, I think we had in this place we had 0.25 omega, then minus tan inverse of 0.2, okay, omega will now be equal to, so this is the phase, right, of J of J omega. So this will be equal to minus 180 degrees. So if we want to calculate the phase crossover frequency, we should set the definition of the phase, okay, of J of J omega and equate it to minus 180 degrees, because it is very true. Looking at this diagram, this line is the minus 180 degree line. So at the phase crossover frequency, you can see that this point is lying on the minus 180 degree line. This is the 0 degrees, this is the 90 degrees, and so on and so forth. This is the minus 270 degrees, this is the minus 90 degrees line. So at the phase crossover frequency at WCP, the angle of our J of J omega is minus 180 degrees because it is lying on this line. Okay, this line is called the minus 180 degree line. So this is the expression of the phase. I hope I got it correctly. Then you have it like this. And if you solve this equation, you'll get minus 180 degrees plus 90 degrees will be equal to minus tan inverse of what? 0.25 omega minus tan inverse of 0.2 omega. Is that okay? So this gives you minus 90 degrees is equal to minus tan inverse of 0.25 omega minus tan inverse of 0.2 omega. If you cancel the minus sign, or if you multiply 2 by minus 1, you have 90 degrees is equal to tan inverse of 0.25 plus tan inverse of 0.2. Okay, that's not so fast. I'm too fast. Tan inverse of 0.2 omega plus tan inverse of 0.2 omega, 0.25 omega, tan inverse of 0.2 omega. So you take the tangent of both sides. Taking tangent of both sides, so tan 90 will be tan inverse of 0.25 omega plus tan inverse of 0.2 omega. So at this point, we need to remember an identity. Let me just copy this and I'm going to paste it up here. Remember the identity. That's tan. Recall, tan A plus B is still the same thing as tan A tan B, tan A plus tan B. Tan A plus tan B is tan A plus tan B all over 1 minus tan A tan B. So this is an identity in mathematics. So tan 90 becomes infinity, right? Then tan A plus B is going to be tan A. So tan inverse of 0.25 omega is going to give you 0.25 omega, then plus tan B, that's tan inverse of 0.2 omega will give you 0.2 omega, then everything divided by 1 minus the same thing will give you 0.25 omega times 0.2 omega. Is that okay? Infinity is still the same thing as 1 divided by 0. okay, or any arbitrary constant divided by 0. So this whole expression ultimately means that this denominator is equal to 0. That's 1 minus 0.25, then 0.2 omega times omega is omega squared is equal to 0. So that's what it means. If something is infinity, then the ratio is some constant divided by 0, making the denominator equal to 0. So you can solve for the value of omega when the denominator is 0. So omega squared will now be, if you rearrange it, you get 1 all over 0.25 times 0.2, and if you take the square root of both sides, omega will now be omega cp, and that's 1 all over the square root of 0.25 times 0.2. Okay, now this is still the same thing as 1 over square root of t1 t2 that we established earlier. Is that okay? That is our phase crossover frequency. So if you can remember when we were defining it, so we define our phase crossover frequency as root t1 and t2, where t1 and t2 are what? Yes, very good. This is your t1 and this is your t2. Is that okay? So I hope you see the beauty of the math. Very good. So let's continue and wrap up. Now we can actually solve this as our WCP will be equal to 1 all over what? So if you see that you don't have enough time to make all these mathematical assumptions and determine this particular expression, you can just use this formula directly to find your phase crossover frequency, which will be the root of 0.25 times 0.2. So let's just use our calculator to solve that. We have 1 all over the square root of 0.25 times 0.2. That gives me a 4.47. Is that okay? So 4.47. So a 4.47 rad per second. So remember, at this point, so therefore the gain or the magnitude of our g of j omega at this frequency must be less than 1, okay, for our system to be stable. So the magnitude should be less than 1. The implication is that the magnitude of j omega, okay, when omega is equal to omega cp should be less than 1. Okay, that's the statement, should be less than 1. So if you remember this particular expression, you can actually get this expression from here. Okay, that's our magnitude expression. So this is the magnitude expression. So if you solve this magnitude by replacing omega with omega cp, you will now get the parameters that you make k restricted in order to make the system stable. But another easier and more accurate way to do it is to remember the general formula for type 1 system. So the magnitude k at this frequency, if you can recall, k is actually going to be k naught this time around. Remember, we have k naught t1 t2 all over t1 plus t2. So this magnitude has to be less than 1. Is that okay? So having determined this particular expression, you can just make k the subject of the formula. K naught has to be less than t1 plus t2 all over t1 t2 for the system to be stable. Now, if you are in a very, very tight corner in an exam situation, sometimes you might not even need to calculate the WCP. If you know this formula for finding this gain, anytime you are solving this kind of question, you can just make this assumption that for our system to be stable, okay, the value of k, that's in our g of s equal to, that's the general standard time constant from S into, you have your 1 plus T1S and 1 plus T2S. So for this system to be stable and for us to impose restrictions on K, then this relation must be true. Okay, this relation must be true. So where this particular one is the gain, is the magnitude of the system at the gain crossover frequency, that's our omega Cp. So just make K not the subject of the formula, and you also have to recall that our K naught was the value of 0.25 times 0.2K. So if you don't remember where we did that, is where we made the substitution when we were expressing in standard time constant form. So all this value over here. Is that okay? So making that replacement and taking note of the value of T1 and T2, will now substitute all these formulas into our expression over here, our inequality. So instead of K naught, I'll have 0.25 times 0.2K should be less than, my T1 is 0.25 plus my T2 is 0.2 all over my T1 is 0.25 times my T2 is 0.2. So if I make K the subject of the formula, K will be less than 0.25 plus 0.2 divided by 0.25 times 0.25 is 0.25 squared, and 0.2 times 0.2 is 0.2 squared. So if you solve this with a calculator, you're going to have 0.25 plus 0.2 divided by 0.25 squared times 0.2 squared. So that gives me 180. I hope we got it correctly. So for the system to be stable, our K has to be less than 108. So this is it. So thank you guys for watching this video. I hope you understood. So this is how to apply the knowledge of all you've been learning so far from Nyquist Criterion up to this point, solving these kind of questions. So this will be all for frequency domain analysis, and I'll jump to the solution of some problems, some basic simple problems, just to wrap up for tonight. Thanks for watching and stay blessed.